Hello, and thanks everyone for joining the webinar today. My name is Jim Bray, and I'm pleased to welcome you on behalf of the Corporate Engagement Office at Northwestern University. Corporate engagement at Northwestern is focused on building mutually beneficial partnerships with companies, whether that's joint work, tackling tough scientific research opportunities, working together to create the workforce of tomorrow, or one of the other many areas of intersection between companies and the university. Today, we're pleased to help launch a new Grand Challenges in Robotics webinar series led by Professor Ed Colgate here at Northwestern, but also highlighting many of his academic and corporate collaborators. I do want to note that we are recording today and that the recording will be available on our site afterwards. So tell your colleagues, spread the word if you find this interesting. My role here today is mainly to introduce Professor Colgate, who will provide a general introduction and serve as moderator for the panel discussion today. He joined Northwestern after receiving his PhD from MIT and is currently the Walter P. Murphy Professor of Mechanical Engineering. His research focuses on touch perception and tactile interface. He has worked extensively in the areas of haptic touch interface, remote manipulation, and advanced prosthetics. And as you will see today, his budding interest in dexterous manipulation. He and his collaborator, Michael Peshkin, are the inventors of a broad class of collaborative robots known as cobots and a suite of technologies for bringing programmable haptic feedback to touchscreens. Professor Colgate is a fellow of the Institute of Electrical and Electronics Engineers, a fellow of the National Academy of Inventors, and a member of the National Academy of Engineering. He's also a member of the Chicago Area Entrepreneurial Hall of Fame. He's founded 3 startup companies, the most recent of which, Canvas, is commercializing innovative surface haptics technologies. And with that, it's my great pleasure to turn it over to you, Ed.
Thank you, Jim. Thank you for that kind of introduction. Well, we're here today to talk about dexterity. Robot dexterity. I think we've all seen some of these news items about robots solving a Rubik's Cube or folding laundry or threatening to replace warehouse fulfillment workers. Yet, human-like dexterous manipulation, it remains a grand challenge in the field of robotics, and many difficult problems remain. So today, we're going to hear from technical and thought leaders as they share their views on the state of the art, some of the key challenges, and the promise of dexterous robots. Before I go further, I should mention that this is actually the first of a series of webinars in this field of robot dexterity. Topics are going to include technical, societal, ethical challenges surrounding dexterous robotics. Here you can see that the next one of these conversations is going to be on Monday, January 30th. It's going to be moderated by Carmel Majidi of Carnegie Mellon University. And it's going to tackle the question of how novel materials are impacting grasping and manipulation. So I hope you can join us for that as well. Also, I want to let you know that today we're going to reserve some time at the end to take your questions. I believe that the Q&A function is open throughout, so feel free to type in your questions at any time. My Northwestern colleague, Professor Todd Murphy, will be monitoring those. So now I would like to stop sharing here and introduce the panelists. So if you guys can all join me, let me say that Kevin Lynch is the director for the Center of Robotics and Biosystems here at Northwestern. He's a professor of mechanical engineering. He's the editor-in-chief of the IEEE Transactions on Robotics. He's also the former editor-in-chief of the International Conference on Robotics and Automation, known as ICRA, its editorial board. He's also the co-author of 3 textbooks, including most recently the textbook Modern Robotics and its popular Coursera courses and YouTube video series. Shuran is an assistant professor in the Department of Computer Science at Columbia University. Her research interests lie at the intersection of robotics and computer vision and explore 2 main questions. First, how to develop perception algorithms that enable robots to interact with the physical world. And then the inverse, which is how to develop, how to leverage physical interactions in order to improve robots' understanding of the physical world. Her lab often studies these questions in the context of robot manipulation. And Russ Tedrake is the Toyota professor at the Massachusetts Institute of Technology, MIT, in the departments of electrical and computer engineering, engineering and computer science, mechanical engineering, and aeroastro. He's also a member of MIT's Computer Science and Artificial Intelligence Lab, known as CSAIL. And he's the vice president of robotics research at the Toyota Research Institute. So let's now get to know our panelists a little bit better. Shuran, you were on a team that won the Amazon Robotics Challenge. Could you tell us a bit about that experience, how you approached it, what you learned, and how it informs your current research?
Yeah, of course, definitely. Let me share my screen so that I can play some videos. Okay, so able to see my screen? Cool. Yeah, so this is actually the video for the Amazon Robotics Challenge. It's the final round for that competition. And indeed, it was actually a very important project to me. It happened 5 years ago, but I think that the reason why it's so important to me is that it really changed, kind of get me into the field of robotics, changed kind of my research direction. And before that, I was mostly a computer vision researcher, that I don't really touch robots. But this project is a project that's really got me very excited about building perception algorithm that actually works for robots. So if we go to the next slide, this is actually the type of things that we're working on today in my lab, where the goal is kind of still trying to build like perception algorithms that allows the robot to kind of see and understand their surrounding environments in a way that they can like safely and effectively interact with them. So as you can probably see in all these videos, we really particularly interested in the type of objects that's not really fit into the traditional definition of objects. So for example, we often work with objects as deformable or like scattered particles like leaves or like fluids like airs. And all of those objects actually is very hard or cannot be easily described with 0-6 poses. And yeah, so in our lab, we often use machine learning methods to model them and in order to support interesting and hopefully useful robot manipulation skills like tossing objects, flinging blankets, or blowing leaves. And that's still what we are working on today. Ed, I think you're muted.
You're muted. You're muted, Ed.
All right, thank you, Shuran, and thanks for that. So let's go to Russ next. So Russ, you uniquely wear two hats, right? You're an MIT robotics professor, but also a senior executive at Toyota Research. Can you tell us how one informs the other, and especially how this relates to robotic dexterity?
Sure, thanks, Ed. No, I feel very fortunate to have those two hats. They enabled me to think about the world in different ways, and I think there's some things that are incredibly accessible in industry and other things that are incredibly accessible in academia. I'll tell you my story in a few videos. So it actually started for me back when I was doing the DARPA Robotics Challenge. We were playing with the early version of the Atlas robot, thinking about the perception, planning, and control for that. And for me, this was an incredibly informative process for me too. I learned a lot about building bigger systems, getting to levels of robustness that I hadn't tried to make my robots achieve before. And we took that into TRI and tried to understand what it would take to take a manipulation system to a higher level of robustness. And I do think there's some questions like that that are just hard to study in academia. And it's very hard to build a system that works 99.9% of the time and be able to put the stress tests on and have nightly hardware integrations and things like this. So that's one of the kind of things that is very much more approachable for TRI. This was a robot that loaded the dishes, did the whole thing from a messy sink. It even at the end will push the button and run the dishwasher. From there, we also, as a part of that pipeline, have been working on developing very high-end simulations. So that actually is a rendered simulation of the physics of a dexterous hand interacting with a plate, and we're very proud about the sim-to-real sort of capabilities of that simulation infrastructure. And these days, I live in both worlds. On the left is some work at MIT, and on the right is some work at TRI, where we're thinking about how to do control of dexterous manipulation, sometimes with simple hands, sometimes with more, but trying to do really good feedback control with cameras and contact in the loop. And we'll talk more about that later.
Thank you, Russ. Really appreciate that intro. And that brings us to Kevin. So Kevin, you've been working in robotic manipulation for many years. Let's tell us please a bit about your work and also from your unique vantage point as the editor-in-chief of one of the leading robot journals, the IEEE Transactional Robotics, sort of how you view the broader landscape. And Kevin, I think you're muted.
Yep, unmuted now. Thanks, Ed. Thanks for that introduction, and thanks for organizing this. Yeah, so happy to tell you a little bit about my past work and some things that we're seeing at TRO. But before that, I wanted to start with this video as kind of a motivation. So here is the process of cutting carrots. And there's a lot going on here. There's a lot to unpack, but I think that this is a good way to introduce yourself to what sorts of problems we study in manipulation. So this is a bimanual task. One hand has a tool, the knife. The other hand is using the bare hand to manipulate the carrot. And if you look at what the knife is doing, it is of course cutting, but it's also sweeping or pushing the pieces out of the way. Both the carrot and the knife are interacting with the cutting board. That's important to stop the motion of the knife and help stabilize the carrot. And then you can see that he's using his hands to roll the carrot on the constraint surface. So nowhere here is an object just being picked up and carried around, which is what we often think of when we think of robot manipulation. So there's a lot going on, a lot of interesting mechanics. And when I want to think about manipulation, I want to start with tasks like this and see how we can break those down into simpler tasks that we might study individually before trying to put them all back together into something as complex as this. So a lot of what's happening here is what I call non-prehensile or non-grasping. So there's no point at which any of the parts other than the knife is being fully controlled by the hand. So you can see in this video some examples going way back to my PhD work of non-prehensile manipulation. So the top left, you can see examples of robots pushing things around, a single object or an assembly of objects. And here you're trying to use the constraints that are available in the environment to help you to perform the manipulation. You have to care a lot about mechanics because you don't have that form closure grasp of the object. But you can do things like control more degrees of freedom of the object than the manipulator itself has. And so you see that in the top right here. This is a vibrating plate happening at high frequencies, creating essentially vector fields on the surface of the plate to drive multiple objects simultaneously. So whether it's sliding or rolling or pushing or mixing them together to do hybrid tasks, all of these are examples of manipulation, useful manipulation without actually having a grasp. And then more recently, we're looking at in-hand manipulation, prehensile manipulation using optical tactile sensors, but now mounted on a flexure that allow us to measure the forces and torques being applied at the contact for things like in-hand sliding manipulation. But all those tasks I just showed were autonomous. We can also think about assisted manipulation because autonomous manipulation is very difficult to achieve. It's something, it's kind of a holy grail we've been working on for a long time. But on a shorter time frame, there's a lot of tasks where robots and humans can collaborate together to solve a manipulation task. And that's what I'm showing here. So this is a group of 3 robots helping by basically canceling gravity on this heavy, awkward payload. And that allows the human to perform the manipulation with the assistance of the robots. And so this is an extension of your idea, Ed, on cobots. So that's all I'll say for now.
All right. Thank you. Thank you, all 3 of you, for this great introduction. So let's get into some questions about dexterity. And I actually like to start by sharing my screen again. Starting with the first questions we need to address, which is, what is manipulation and why is it so hard? Why has progress been so slow, particularly when compared to areas like legged locomotion, aerial vehicles, self-driving cars? So as an example, I go here. Here is a video from a really nice paper, in fact, an award-winning paper from ICRA, that robotics conference, 2016, so just a few years ago. And it's a paper that explored ideas of machine learning for in-hand manipulation. But let's compare this to these videos, which come from the work of Ken Salisbury, the famous Salisbury hand, in 1982, 40 years ago, right? And again, I didn't mean to take nothing away from either piece of work. There's a lot more going on under the hood than just what we see in the video. But at the surface, they're certainly remarkably similar. It just doesn't seem like we've come all that far. So let me start with you, Kevin. What is manipulation? What is dexterous manipulation? What makes it so hard?
Yeah, great question. As you said, there's a lot going on under the hood in those videos that we're not seeing, but at the surface, you ask, why are we so far behind in robot manipulation? So we see some of the incredible things coming out in legged locomotion, and legged locomotion shares a lot of characteristics. Both cases, you establish and break contacts. They're intermittent, they're dynamic. So in manipulation and in legged locomotion, you have both of those things going on. So why is it that we're not seeing the, essentially the Boston Dynamics videos of manipulation? I think one difference is that I'll be a little controversial, but I think we've mostly agreed on what the objective is for legged locomotors, and that is that they should get from point A to point B and they shouldn't fall down. And I think, the robots could have 2 legs or 4 legs or more. The ground could be flat and hard, or it could be yielding, it could be sloped or stepped or rocky. But effectively, the objective is to transport or reconfigure the robot in the world. So there's been a lot of research effort towards that goal, but I think in manipulation, there's been much less convergence on canonical benchmark problems. One exception might be sort of multi-fingered grasping, right? How to place fingers on an object so that we can carry it around and then ignore the kind of nasty dynamics and contact mechanics. But I think as a result, if you look back at that carrot video, manipulation research has been spread over lots of different problems, and it's difficult then to assess our progress because, we haven't agreed on a single set of problems. And I think, in addition to that, manipulation is just hard. You might have one or multiple objects. They could be rigid or soft or flexible. You might have fixtures or external constraints. Contacts are breaking all the time, and your actuators are only connected to the objects that you're trying to control through kind of messy contact mechanics where uncertainty is everywhere. So, I think the problem is hard. And the second issue is that we just haven't agreed on a small set of canonical problems that sort of drive the field forward in a measurable way.
Okay, that's an interesting perspective, but let me turn it to Russ, who's actually done a lot of work, as he showed us, on the legged locomotion, which you talked about, as well as the dexterous manipulation. So Russ, what do you think about that perspective? Is that fair?
Oh, well, I love what Kevin said, but I'll just try to be contrarian a little bit just to keep it interesting. I definitely think manipulation is a controls problem. That's how I'm wired to think about it. And it's tempting to say that the rules of the game are governed by mechanics, but I actually think the reason it lights me up is actually because manipulation is so much more than mechanics. The rules are not just in the equations of motion. I'd like to just start with the equations and say, here's my task and solve it. But actually, the way we pick things up, the way we move through the world, whether we should even pick something up, has so much more to do with perception and the diversity of the world and what are reasonable things to do, and what even some notion of common sense, right? That it's asking our control tools. For me, the challenge is to bring our control tools up to a higher level of intelligence and understanding and the like. From a controls perspective, it really, I feel, almost embarrassed that we haven't got better solutions, but it should be easy. Like, by all accounts, I mean, there is uncertainty, there is contact, there is making and breaking, but we're not in a regime where we're at the limits of control authority, or we're like marginally stable or anything like that. By most control metrics, this should be an easy problem. And I think we need to still discover exactly why that's easy. But I think, and just maybe to speak to the Salisbury hand, which is an awesome video, I think there's a difference between a targeted demonstration, which we've been able to do forever, right? And a fully general autonomous, you give me a new problem, I can synthesize a controller in just a minute. That's the dream, would be that I could synthesize brand new controllers for all a diversity of tasks. And that dream is still unrealized.
All right, I appreciate that perspective. So it should be easy. Shuran, what do you think about that?
Yeah, I think this is a really good question to get started. And I think that's also a question that I think a lot about. It's like, what's the difference between, for example, locomotion and manipulation, and why we can do so much progress on locomotion, but not on manipulation? I really feel like, I think my perspective, maybe Russ don't agree with me, is that the complexity of the model. So what the things that you're trying to model, right? In locomotion, the things you're trying to model is mostly the robot itself. And a lot of estimates you can easily get internally. And the environment impacts can be modeled with external forces or abstracted by like external forces. But in manipulation, we're really trying to like interact with the world, and the complexity of modeling the unstructured environment is so much bigger, like harder, right? And then that's why like perception plays such an important role in manipulation, but not too much in locomotion. So I think that's like why these two problems is so fundamentally different, and maybe like one is much harder. Yeah, that's my take.
So if I could, build on that just for a moment, you've done a lot of work, Shuran, in dealing with some, as you showed in your video, some environments like shirts or rope that are indeed difficult. Difficult, I would say, not just to model, but maybe, and I'd like Russ to respond to this, maybe also to control, not in the sense of you're at the limits of stability, but in the sense that you're highly underactuated compared to the vast number of states of the environment. So is that an aspect of it that we maybe we lack some of the control authority in manipulation tasks?
I think we can definitely benefit from progressing control for those very challenging tasks. But I also feel like there is something about just what is the right representation, how much we need to model. I think, for example, for ropes or deformable objects, it is like everybody agrees very hard to model, but we can manipulate them pretty effortlessly every day. And it doesn't seem like to me that we have a perfect model for those objects, right? So a lot of times we rely on some kind of intuitive physics or like kind of intuition to interact with those objects. So maybe we just didn't find the right representation or like the right way to represent all those complicated things. Instead of like, we need to have a more precise model or control method for it.
Russ, do you have more to say on that topic?
Yeah, no, I think the examples are good, right? So the flipping a towel out or something like this feels like a very different problem, which the model is very underactuated and all the good stuff. A lot of dexterous manipulation that would be incredibly useful isn't as underactuated as that, but it's still hard. Like just putting dishes away feels like a problem where there's so many solutions that would get the job done. The search space, should be forgiving. The control authority is absolutely not there. I do think that you could even argue that's true for the towels. Like humans probably wouldn't be very good at it if it was a really super, if it required only a very narrow possible trajectory to be able to accomplish the task. But I do think that one's harder than I would say the lion's share of dexterous manipulation in my mind, which is happening all the time when I zip my my jacket, when there's all kinds of things we do all day which are very dexterous. I think we underappreciate how often we are using our very dexterous hands, and most of them should be easy.
Kevin, I wonder what your thoughts are on this topic.
Well, I appreciate Russ's assertion that this should all be easy. That just makes those of us who have been working in this area for so long feel even worse than we already did.
Me included.
Yeah, I agree with what Shuran said in terms of the complexity of modeling. And so the question, and maybe we'll talk about this a little bit later, is, what is the value of modeling in real world manipulation tasks? So, for my own work, a lot of my work is based on having good models. And if you don't quite have good models, then learning a representation of the models, but in a parametric way, because I want to take advantage of what we know about physics, right? We don't want to just throw that away. So I think, one of the key challenges here is figuring out how to use what we already know about the world with a very limited number of experiments, because experiments in the real world are expensive and slow, possibly with simulation to come up with appropriate control techniques. And I think that's one of the sort of grand challenges of robot manipulation that really gets called out because of the complexity of the environments that we're interacting with.
Thank you. Let's turn to some of Shuran's work on the Amazon Robotics Challenge, which really had to do more with grasping. I view grasping perhaps as a subset of dexterous manipulation, but grasping in very complex, cluttered environments. And I wonder, Shuran, if you can say a bit more about what some of the challenges were that you faced in tackling that problem.
Yeah, I think grasping probably a lot of people consider is one of the easiest like manipulation tasks, or at least it's one of the first tasks if you want to interact with objects. I think grasping is probably the first thing coming to our minds. And yeah, so I think for Amazon picking challenge, a large part of it is trying to grasp objects. And I think one of the biggest challenge is that we don't know the objects beforehand. And the object is very unstructured. It's just dumped into a bin, and it has it's get on top of each other. It has heavy occlusions. And I think in terms of the system building perspective, I think really the biggest challenge is how to make it robust. I think similar to what Russ said for the DAPA challenge. If you have a system that you're going to enter a competition, you want to win, it's really you want to make sure that it works all the time, or at least work most of the time, because it only has one shot on it. And I think so it has a lot of challenge on both perception and planning. But back then I mostly work on the perception part, and I think my experience working on the perception part of the system really teach me two lessons that I think is interesting to share today. I think first part is that I realized that it is much harder to actually build a vision algorithm for robots, or for physical robots. Right? I think that's not surprising, because we need the perception algorithm to run fast, need to be precise, and they also need to be robust to noise, right? So typically, for example, pulse estimation, if you have 5 centimeter error, it's actually considered okay in typical perception benchmark, but it can just crash a robot into shelves, and that's not good. So that's one lesson. And the second lesson is actually the opposite. Is I realized that sometimes building vision system for robots can be easier than developing vision algorithm itself. So that feels a little counterintuitive, but here is an example. So we know that recognizing the objects in the cluttered bin, or doing pulse estimation, is very, very hard. That's probably still very hard today. It's still open challenge today. But what we learned or realized later is that you actually don't need to do pulse estimation for the objects to grasp it, right? A lot of grasping can be just inferred from geometry alone. And then once you grasp the object, once the object is in your hand in isolation, it's almost trivial to recognize it. So by leveraging the ability that robot can grasp the object, really simplify the perception problem. So I think that is a very interesting lessons I learned from the Amazon Robotics Challenge. Is once you have this very complicated system, has multiple parts, it's kind of very important to think about how different parts can help each other or work with each other, so that you can get a very robust system.
That's a beautiful answer, and a beautiful illustration of how manipulation can aid this very challenging perception problem. So that competition was sponsored by Amazon, so I want to talk a little bit about the state of this technology in the commercial world. So I think, Russ, you're partially in that commercial world, and I know you're doing amazing things at Toyota Research. Amazon, of course, is working on manipulation. We see things about the Tesla humanoid robot, and there are many others who are actively working on dexterity and surrounding problems. Russ, is it nearly on us? Is this nearly a solved problem?
Oh, that's a good question. I think there are applications where our technology probably isn't far from, I think maybe it's a lot like autonomous driving, where you can imagine there are some problems that will be hard for a long time in the corner cases, but there are some use cases where you geofence and you work just on the highways or something like this where it could work. I think the same thing is true in manipulation. I think probably the last few years of really rapid progress of, I think, connecting perception and basic planning manipulation will enable a lot of logistics, is enabling a lot of logistics type applications and slightly more flexible automation and the like. But I think we're still a long way from the robot in the kitchen chopping carrots like Kevin asked for. So I'm optimistic that there's a runway of increasingly complicated challenges that will require more and more dexterity. But I do think the hard problems are still, even though it should be easy, I think it's going to take us years to get there. Yeah.
Okay, so it's sort of, an analogy to autonomous driving. Perhaps there are sort of levels of autonomous dexterity in robotics. Kevin, what are your thoughts on that? Can you imagine the prospects of us sort of coming together as a community and defining or agreeing upon what some of these levels might be?
Yeah, I think, the sort of dream of the fully dexterous robot, whatever that means, is long in the future. But there's a lot of big wins that we'll see before that. One thing I'd like to point out, and this was also a motivation behind the Robonaut project that NASA had, where they were going to put a robot up in the space station that can work in a human environment, and also in the DARPA Robotics Challenge, is that, as long as we humans are sort of inhabiting our physical bodies and not downloaded into silicon or something, there's a lot of infrastructure around that's already been developed for us to interact with, doors, tools like the knife or scissors or screwdriver, whatever. So even though, there's a lot that we can do short of creating robots that are sort of human-like in their ability to manipulate, there is some drive for in the future to achieve that, so that they can take advantage of the tremendous infrastructure that already exists and will continue to exist in our environment. So I think that, as a community, it's difficult for any individual researcher, or certainly any company that needs to scale a manufacturing process in the near term, to think about how to achieve this more dexterous vision that we might be shooting for. But I think if we, come together in a convergent effort where we've got, novel multifunctional materials, new tactile sensing, bootstrapped machine learning, simulation, more densely packaged actuators, we can make progress towards, potentially a future human capable hand, or superhuman. There's no reason we have to stop there. And certainly with, electrosense and other near field sensors that we could equip the robot hand with, there's no reason that we have to stop there. But I do see that there is going to be a motivation out there to look for more, anthropomorphic solutions in the distant future.
Terrific. All right. Well, I appreciate that. So we've talked a lot about dexterity, the sort of the nature of the problem, why it should be easy, but in fact it's really challenging. Let's start drilling into some specifics, and I'd like to start with artificial intelligence, right? So we live in this age of deep learning. We see in the news all the time really amazing successes, like large language models like ChatGPT that everyone is seeing these days, or drawing programs like DALL-E. There's also a lot of excitement about AI and robotics. But those big successes in the news are mainly in areas where there's an extraordinary amount of data readily available to train these very, very large models, right? So this is mainly text or images from the web, right? And robotics it isn't, I don't think it's like that, right? So I wonder what your collective view is as to whether these large AI models are going to revolutionize robotic dexterity. And if so, where's all that data going to come from? So, Shuran, would you mind kicking this off?
Yeah, so I think that, that's a very interesting and timely question, actually. Okay, I want to divide this question into two parts. I think the first part is for all this large model, or some people call it foundation models, that's trained on internet scale data. So first question is that whether they are directly already useful or relevant to robot manipulation, right? Is there a way that we can already use that? And the second part of the question is that, do we need a robotic or like a robot specific type of foundation model? If so, what it should look like, what's the input and output for that, and where we should get data? Okay, so I will maybe first just answer the first question, like why, how the current foundation model can be relevant, right? So if we just provide a little bit of background, if you look at all the foundational models, I think right now there's two popular types. One is this large vision language model that's trained on internet images and captions. And the other is like language models that's just trained on text. And then I think for the first large vision language model, it's pretty easy to imagine how it's relevant to robots, right? It's basically providing a better perception model. You have a better perception model that's able to understand visual concepts beyond standard data set like ImageNet, because it's trained on internet scale data. So I think that's easy to argue that it's relevant, it's useful. And I think that the more tricky part is for the language part. So for a large language model like GPT, like ChatGPT, they train only on text. And I think the first feeling is that how can a model like that be relevant to manipulation, right? So we typically don't describe our low-level like manipulation or like those subtle actions with text. So are those models still useful? I think my answer is yes, it's relevant. It will be helpful, but it's not like directly replacing, but it's providing some complementary information or like functionalities. I think we already see like two types of ways of how to use those models. One is that those large language model can be used for planning because it has a lot of common sense information. So if you have a new task, you can ask ChatGPT to give you a step-by-step instructions on how to do it. It's high level, but it's already useful. That's one way. Another way is that people realize that the large language model can also write code, right? They also like code is another form of text. So there's another word called like code as policy. It's like you can actually just ask those large language model to write robot code if you give them the right APIs. And because there's a lot of robot code shared on GitHub, they actually can write non-trivial functions like pick and place, or like even I think I see an example of doing like PID control for like carpool tasks. So I think that's another way that it can potentially helpful. But I think it doesn't really replace those kind of low-level control algorithms or like kind of learned visual policy that really learn from robot data, like interactive data. So I think the second part of the question, I really want to hear Russ or Kevin's ideas. Do we need another type of foundation models for robots and how it can get the data? Yeah.
Russ, you want to pick that one up?
Oh, I was going to go on the first one too. That's such a good topic, but yeah, no. So I completely agree. I think that once ChatGPT came out, but even a little bit before that, people started asking task level reasoning type of questions for manipulation of these chatbots and getting surprisingly good answers, and starting to think about ways to map the relatively unconstrained output back into actions that the robot can actually execute. This is unquestionably going to change what we do. And it's hugely surprising to me, because I would have thought that some of the AI level discrete planning would be some of the harder stuff for the deep learning methods to tackle. So it's incredibly good. I do think it actually puts a premium on some of the lower level, more, the more straight up dexterity, because now lots of people can look at ChatGPT and get a list of like, oh, to make a pizza, I need to go to the fridge, I need to get the dough, I need to roll the dough, but then somebody's got to make the robot roll the dough, and those problems are not in the large language models. So I'm actually optimistic that it will make our work even more important, I hope. So, but I like the revolution is here. It's amazing what the implications of that technology.
Kevin, want to?
Yeah, I think the thing that will allow these models in different domains, perception and manipulation, to come together is an ability to talk to each other. So thinking about representations. So one of the Shuran had a great example there. Like, to pick something up, you don't have to necessarily first estimate its pose to pick it up, right? And but if you're thinking about the problem in the abstract, that's probably what you do. You're going to break it into pieces. You're going to define what the representation is that goes from one module to the next module. Perception module gives this, goes into the grasping module, which figures out where to put the gripper or something. So in some sense, if you've done that in advance, you've placed constraints on how the system can work, and you've made the problem possibly harder for yourself, right? So that's kind of the model-based way of thinking about it. On the other hand, you have to have representations so that you don't just have, the problem is everything, right? We're going to, take all inputs and control all outputs and see everything that happens. We're going to learn everything, right? So you're going to have ways to have different modules that have different capabilities at the low level, like the rolling the dough module, be able to talk to the large language module. And so, whether it is hand coded or learned or some other way in between, I think it's the representations at these different levels of the hierarchy of these complex tasks that we're going to have to think hard about. That's going to, allow these different capabilities to work together.
Right, that's great.
If I can just add on, I think I really want to push on the question of like, what is like do we need a foundation model for robots? Like what will be the data looks like? What will be the input and output? Because that's something on my mind. I really want to hear your guys' thoughts. Yeah.
Well, I guess we didn't quite answer that, did we? So do we want to go a little more at it?
Yeah, for sure. But Shuran, you've thought about it a lot. Let's hear your thoughts first, and we'll respond.
Oh no, I actually don't know. Like that's why I'm asking this question. I feel before, if you ask me, I really feel like the interaction data, like self-supervised data collection, if the robot can collect all the interaction data and it can self-supervise with future states, then it's one of the ways that we can get a lot of data and it can be the foundation model for robots. But I just feel like the disadvantage is so clear, right? We only have so many robots and it can only collect data in real time. It's expensive, it's gonna break. It feels like never able to compete with those internet data. So do we need to recompete or we just like, I don't know, yeah.
Let me interrupt and say, you're right. We can only do that, in real time with robots, but of course we can do it much faster in simulation. And I know you've done a lot of really nice work with sort of sim to real. So what do you think about the prospects of getting the data through simulation?
I think, yeah, simulation is definitely an easy way to get more data, but I don't think it has all the richness of the real world data that we can get. And maybe, like for example, if we have the simulator, the data that we can get is as good as the model or the physics model that we have, right? It cannot go beyond that. But as we already discussed, a lot of manipulation like in the physical world is about the subtleties that's hard to write a physical model about. So I still feel like there is a much bigger value, at least to me, to collect data in the real world.
Okay, all right.
So, okay, I'll go on that. So I think the fact that we feel data limited in robotics is very real, but isn't that a short-term problem? I mean, can we just be optimistic and shouldn't we be working on the case where we have robots everywhere and we made one more robot, the N+1th robot, and it has the benefit of all the learning and experience that all the first N had? That seems like a qualitatively different problem. I think it changes the way you think about control. I think solving a control problem of planning through contact with pixels from scratch every time is proving to be pretty challenging for our techniques. But if it's like, well, I've already solved these N control problems and I've got a new object that's only a little bit different and I have to, carve out one more skill, that feels like a pretty different place to be. So I don't know, I'm optimistic that we will eventually get the data. And I think we have to be creative about ways that we study those questions before the data is available. But the robots are coming, the big companies are putting out robots so fast, yeah, it's not that far in the future, I think.
Okay, I hope.
So Russ, what you just described actually sounds like a foundation model for robotics, right? This future where we are really only planning for the N+1st task. It sounds like that N, isn't that a foundation model?
Yeah, I mean, we could argue about exactly what it should be called, but I think I absolutely think there's something about being able to extrapolate across just massive amounts of data that if we think about it at the level of a skill, I do think that would be something that would be hard to get from scrubbing the web, that would be somewhat more robot manipulation specific, that would just have a similar massive possible impact. So I'm all for it. Let's do that.
Okay. We're getting close to time when we need to go to Q&A, but I really got to get in at least a question about touch, because that's my whole existence is trying to understand touch and display touch information. And so let me start with Kevin. So Kevin, you've said to me before in private conversation, right, that yeah, no more private, right? That you view one of the great challenges of dexterity is sort of unlocking what humans already know how to do, right? Where we are, as you showed in your carrot video, we are dexterous. And so we've talked a lot about how do we access that, right? I mean, we can access language and images, through the web, but how do we access humans' ability to interpret and act on and touch information and use it in control? So I'm curious, how do you imagine that sort of thing playing out and benefiting robot dexterity?
Yeah, I mean, with the caveat that this is clearly anthropomorphic thinking, right? Because that's the way we're wired. I guess the idea that you're referring to is, sure, we're extremely dexterous with our hands. We can do lots of different things, very general purpose, and it's all locked up in here and in our structure. But how do we get that out? How do we learn that? Because we don't have direct access to the data, to the representations. So one possible approach, and this is where people who can do good tactile sensing and haptic feedback have a large role to play, is if we can create somewhat anthropomorphic robot hands that are capable of sensing the environment, providing the similar sorts of sensors that the human has available, and then relaying that information with low latency to a human hand. Maybe there's a way that we can actually gather that information, the stuff that's missing right now. If we're just watching somebody, and this is the classic programming by demonstration idea, that you watch people solve tasks and you try to get robots to do the same thing. Well, you're missing all the tactile information, most of the force information, and lots of other stuff. So is there a way we can kind of tap into that process by having a robot over here performing a task, a human over here feeling what the robot's feeling, and a tight coupling between the two of them, where we have access to all of that data, where now we can start doing machine learning on richer data as opposed to just vision data, for example. So I think that's obviously a huge challenge, how you create those transparent haptic feedback for the human and otherwise couple, but I think it's an exciting potential future area.
All right, well, thank you. I've got a whole lot more questions I want to ask you all, but so does the audience. And so we're going to turn now to some questions. As I mentioned, Todd Murphy has been monitoring, and he's given me a few questions here that I'm going to relay to you. So this first question comes from Jimin Hong, who's a research engineer at Hyundai Motor Company, and is here. Let's see. He says, what would be an ideal integration of reinforcement learning and traditional motion planning to improve hand dexterity? Russ, maybe you can start us off with that one.
Happy to take that one. So it's a great question. I think RL has showed some things that are easy, or some things that have worked incredibly well empirically. And what I'm super optimistic about is that people are now, we have, for instance, very strong theorists coming in, maybe partly from control, partly from machine learning theory. They're coming in and understanding the fundamental questions there about why reinforcement learning has worked when it worked. I think reinforcement learning itself has a lot to give, but I think the best stuff is going to come from when we understand some of the core technologies behind reinforcement learning that made it successful, and marry them with the more model-based planning and control, right? And I think the two obvious places where control has struggled, where reinforcement learning has succeeded, has been dealing directly with pixels, and then dealing with all the discontinuous contact dynamics. And I think we're digging in now, and we're understanding better the reasons that RL has been successful at times there. And I think many of those lessons will marry directly back into control, and we'll have more efficient, sample complexity results and strong results from that.
Terrific. Could you just, I don't know if I should do this in interest of time, but can you say a little bit more about why the RL approaches have been more effective at dealing with discontinuous contact? That would strike me as an area where you would expect more traditional mechanics-based approaches to be successful.
Okay, so here's a specific result that we've been thinking about here, which is it turns out that the type of randomization that people put into an RL algorithm just for exploration, you just try to put random noise on the output, it has an interpretation of smoothing the mechanics. So it actually, it's almost like taking your discontinuous cost function that comes from that happens due to discontinuous mechanics, and it's just taking a low pass filter over there. And that has pros and cons, but it changes the optimization landscape in a way that gradient descent often is more successful. Now there's pitfalls of that too, because you're learning on a different landscape. And there's times where you'd like to, you can be faster with the model-based in the nice smooth areas. But in the places of hard discontinuity, RL has done something very clever. And we can bring those two together and try to get the best of both worlds.
All right. Thank you. Thanks for digging into that a little bit deeper with me. So we have a question. Actually, to be honest, I'm not quite sure who it's from, but I'm going to ask it. It's a great question. And I'll ask Shuran to address it. And that is, what is the current state of common benchmarking for robotic dexterity? There's a lot of activity in grasping, but likely much less for dexterous manipulation.
Yeah, I think that is a really good question. I think we mentioned it in the very early on. One of the reasons that's why we feel like we didn't make like a whole lot of progress is because we don't have like a shared goal in mind for manipulation. I think it has both its pros and cons. I think having benchmark, I think we already see a lot of effort on that. There's like RL bench, MetaWord, like there's a lot of simulation-based benchmark that is designed for manipulation, and a lot of them is actually dexterous manipulation. That dealing with pretty complicated tasks. But often criticism is that those are not, they're simulation based, they're not real world. But once you start to think about real world benchmarking, it's like there's a lot of practical issues and difficulties. I think Amazon Robotics Challenge is a good example, but we can also like see that there are so many like issues that it's very expensive to actually run those kind of benchmark. Right? So as a researcher, as a research lab, you may not have all the resources to do that. But we still need a benchmark to measure progress. So I think there is a lot of good discussions about what should be the benchmark looks like, how we can make it like credible. That's all the community as a whole can agree upon, so that we can measure progress. I think it's still an open discussion question, and if anyone has opinions or ideas about it, I'd like to hear that as well. Yeah.
Okay. Yeah, benchmarking in general is it's incredibly important, but very, very challenging in areas like this.
And you also need to have agreement by a sufficient mass of people, critical mass of people, to say, yes, this problem is important enough that this should be benchmarked instead of those other things that I could have been working on. That's
true, yeah.
We've got a lot of questions coming in here. So I'm going to turn to one from Tasha Brazier. And I'll ask Kevin to respond to this. And Tasha asks, how many sensors would be required for a robot to get enough information to make decision-making AI work? And so I turn that to you because you've been talking recently about the tactile sensing on top of the image-based sensing. So
sure. Yeah, again, if you're solving a specific problem, oftentimes you don't need any sensors at all, right? So if my problem is that this object should be on the floor, well, just push it and I know it'll end up on the floor or something. So I think, if you're talking, so one end of the spectrum to look at, and it's not really the end of the spectrum, but one point of the spectrum is, what are human capabilities? What sensors do we have? And do we need to endow robots with the same kinds of sensors? And maybe the answer is, if you want to do everything that a human does, maybe the answer is yes. But in the end, we always work on this task. We're going to check our performance on this task or that task. And I think specific people like me and others who've worked in minimalism, we care a lot about what's the smallest number of sensors or actuators that we can use to solve this problem. And so I think it very much depends on what your tasks are. And so one default is just to think about everything a human can do. And the other default is usually this task or that task. And oftentimes they can be solved by very simple solutions. And that's what we do, for practical reasons in industrial problems.
I always like to say that if you give me one of those robot claws, the $2 robot claws from the toy store, I could probably do a lot of useful things in the house with that thing. So I can't blame the hardware, but better hardware, better sensors would make things easier, right? Should make the problems easier. So.
All right. We are fast coming down to it, but I want to end on a question from someone you all know well, Matt Mason. And Matt asked a challenging question for us. And he asked, is it possible that the focus on grasping and dexterous manipulation is distracting researchers from other problems, other capabilities? If so, he wants to get a jump on everybody. So what are those next problems and capabilities that we should be working on? And if you can't name them, then how do you dream up a process for identifying them? So taking us beyond grasping and manipulation, perhaps. Any thoughts? Are we distracted here?
I don't feel distracted. I think that this is, for me, I mean, Matt knows I came from legged locomotion towards manipulation. And for me, this is the right problem that is a bridge between the control theory I know and love and common sense, general AI. It gives me a suite of problems that are in that transition mode that I can think rigorously about, but try to get out of my comfort zone a bit. So for me, it's a great spot. Now, do you need a dexterous hand exactly to do that? I think it's a good choice for that. I don't feel distracted. I'm happy to do what I'm doing.
Awesome. Kevin?
Yeah, so no, it's not distracting. It's extremely rich, but it's hugely potentially impactful. I mean, this is the business end of robots. This is where the robots that otherwise just move around and flail actually cause the world to change, right? And so that's what we want from robots. We want them to manipulate the world, reconfigure the world, not just reconfigure themselves, but actually change the world for us. And that's going to happen at the contacts at this, where dexterous manipulation happens. So I find, it's daunting, challenging, open-ended, ill-specified and all that, but extremely exciting.
Wonderful. Shuran, I'm going to give you the last word.
Yeah, I totally agree. I think it is like, I cannot think about other things like as other than manipulation as the most important thing to address in robotics. I think that's really what adds the most key capabilities to our robots. And also I think it's kind of like scary for this question come from Matt, but I remember when I just started like doing dynamic manipulation, I read so many papers from Matt Mason, and I remember when he described dynamic manipulation, I think one of the sentences kind of like, it may not be that useful, but it's beautiful. So I think I think first of all, I totally feel like it's very useful, but also I think it's very beautiful because if we understand how human manipulates or how to manipulate object properly, it gives us more than just a good robot system. It also gives us a better understanding about potentially like human learning or human cognition or like a lot of other things as well. So I think it's a very valuable problem to study.
What a wonderful way to end this conversation, Shuran. It's useful and it's beautiful. And I think we would all agree. Dexterity presents us with really some beautiful challenges and problems to work on. And as Kevin pointed out, an opportunity to have huge impact in the world. So I can't thank you all enough for sharing your time, your wisdom, very, very hard-earned experience with us here today. I think it's been just all that I could possibly hope for in kicking off this series. I do want to remind the audience, I'll share once more, that we've only just begun, and we do have another webinar coming up here in a couple of weeks on this topic of novel materials for robust grasping and manipulation. And I believe that Jem is going to come back and close this out. And I just want to thank the audience as well for being a part of it, for submitting your questions. I know we could hit only a few, but thank you for being engaged.
Hey, thanks, Ed. And thanks again to all the panelists for a really fascinating conversation about robotic dexterity. Also, a big thank you to our team behind the scenes, making sure everything went smoothly today, Sonia, Brandon, and Kate. And thanks to all of you who have tuned in for today's session. One quick word before closing, before you leave, we have a brief survey. We'd really appreciate if you could fill it out and provide us some feedback. Survey is really important to us. It should only take a minute, and you should see the link in the chat box. If you're interested in learning more about what you've heard today, please don't hesitate to reach out to Ed. Or if you're interested in learning more about corporate engagement at Northwestern, you can check out our website at corporate.northwestern.edu or contact me at j-bray@northwestern.edu. For those that might not have tuned in before, our office hosts a quarterly webinar highlighting some of the different research areas around campus that may be of interest to companies. We've partnered with Ed to launch this new Grand Challenge in Robotics series, and definitely hope that you tune in for the next one on January 30th. But I also want to invite you to check out our next regularly scheduled webinar on March 9th, which will feature Professor Danielle Tolman-Ersick, who will talk about building biomolecular devices, highlighting collaborative work from our Center for Synthetic Biology. So very different topic area. Until then, and until next time, take care and enjoy the rest of your day.
Right.